continue with this. So this is an interesting relationship. Let's look at it in a slightly different way. This was our Carnot cycle. Now, in this Carnot cycle, Q1 is the heat taken by the system during this time. Q2 is the heat giving out by our engine during those two adiabatic processes. Let me imagine the whole process as a collection of very infinitesimal steps. At each step, I allow the piston to expand, either expand or compress by a very small amount. So these are my, let's say, very small steps. At each step, let me call the heat taken by the system. Let me just look at this step. During that very small amount of step, let's say that I give to the system an amount of heat given by this dQ1. With that bar, it's not the differential to denote that it's not the differential of anything. Now remember, let me also label these points. If I sum dQ1 as I go from A to B, that will be the total heat taken by the system. So this is Q1. If I sum as I go from C to D, this is minus Q2, minus because Q2 is the heat given out of the system, whereas dQ, sorry, not 1. Let me ignore the 1. dQ is the heat given to the system. If the system is giving heat outside, then dQ is negative. And Q2, I defined that heat to be a positive quantity, the positive amount of heat the system gives outside, that corresponds to minus Q2 heat given to the system. And as I go from, let's say, B to C, you see B to C is adiabatic. There's no heat exchange. So dQ is 0. And similarly, as I go from D to A. Now, as I go from A to B, the temperature is fixed, T1. So this is isothermal at temperature T1. This is isothermal at temperature T2. So let me divide this by T. At each step, I am summing the heat given to the system by the temperature of the system during that step and summing them all up. But as I go from A to B, that is just T1. As I go from C to D, let me divide by T again, it is just T2. As I go from B to C, temperature changes all the time throughout the process. But that doesn't matter because dQ is 0. The system is isolated. There's no heat exchange. Similarly from D to A. Now let me sum all of them up as I go from A to B to C to D. dQ by T. Again, I repeat, during this cycle, and D back to A. During this cycle, I divide this cycle into very small steps. At each step, dQ is the heat given to my system, and T is the temperature of my system during that step. Since the step is very small, even if it's an adiabatic process, the change in the temperature will be negligible. So I can identify a temperature of the system during that very small step. So this is a well-defined quantity. I can even measure it. But this will be nothing but Q1 over T1 minus Q2 over T2. Just sum all these four numbers. But remember this relationship. That difference is 0. Now, if I imagine these very small steps, when I take the limit as each one of those steps goes to 0, this is nothing but an integral. Over the loop, that's why I put that O sign, of dq divided by t, this is equal to 0. At least for the Carnot engine, the integral of dq over t is exactly equal to 0. Well, Carnot engine is a very special kind of engine. So the first question is, how general is this? Well, let me imagine an arbitrary process. This is my arbitrary process. I give some heat in order to be able to change the PV along these lines. As my system is expanding, I have to give heat, take heat, but let's say that I somehow manage to arrange that such that my engine follow this trajectory in the PV space. And it's just a cyclic process, it can repeat itself. This is just another engine. Not necessarily the Carnot engine, but some other engine. First, let me prove that this equation, that the integral of dq over t over this closed loop for this engine is also 0. Although it's not the Carnot engine, still for this engine, that integral is 0 over an arbitrary loop in the PV space. Now, how do I prove that? Well, basically, I divide this into very small Carnot engines. Let's say that I run a Carnot engine along this line. And then another Carnot engine along this line. Another Carnot engine along this line. Over here. And over here. And also here. I'm just imagining some other hypothetical Carnot engines. So if I try to calculate, you see, why do I imagine these Carnot engines? Let's look at the non-overlapping parts. Well, non-overlapping parts is this blue line. You see that blue line almost follows my arbitrary path. If I choose smaller and smaller Carnot engines, thinner and thinner, then that blue line will exactly follow my arbitrary loop. Are you convinced? So when I evaluate this dq over t over my arbitrary path, my claim will be this is equal to sum over all these thin Carnot cycles This is what I will claim. Why is this so? Well, I mean, if you look at each one of those Carnot cycles in that integral, let's say, if you look at this Carnot cycle, there's a contribution from this part. this segment. There's an adjacent Carnot cycle, there's a contribution from this segment. Both of those contribute to this dq over t. But if you are absorbing heat during this process, you are emitting the same amount of heat if you go the other way around. So basically, as your system goes along this line, your Carnot engine takes heat, but as you are going along that line, your Carnot engine gives away heat. So basically, the contributions from these overlapping lines, one will be positive, the other one will be negative, and exactly the same number. They will just cancel. But if they cancel, then this equality over here is correct. But if that equality is correct, each one of those terms in the summation, this is 0. So this is 0. So we can conclude that, just imagine any engine running some gas, some solid, it doesn't really matter. The only thing that is important is at each point during its cycle, it's in equilibrium. So we can talk about its pressure and volume at any time during its working cycle. For this arbitrary engine, dq over t is always 0. Now, why is this important? Well, do you remember anything about forces that looks similar to this one from mechanics? Yeah, there's a conservative forces, which tells you that if around the loop the work done by a force is 0, then it's a conservative force. And the more important thing is that if there is a conservative force, then you can define a potential energy, which depends only on the state of your system, not on how you reach that point. You see, we cannot define a function q. So let me first define the entropy. This is equal to, from the point A to the point B, dq by t. This is how we define the entropy. If you remember, this just looks like the definition of the potential. If the loop integral of a quantity is 0, then if you integrate that quantity from one point to the other point, that integral depends only on the endpoints. It does not depend on how you go between the endpoints. Yeah. I have an integral dq by t from A to B. That integral depends only on the endpoints because the loop integral is 0. And hence, I can always write that function as the difference of two values at the endpoints. Now, why is this so? Well, let's just imagine point A, point B. I can go along this path or along this path, let's say path 1 and path 2. Well, what this tells me is the integral of dq by t as I go from A to B along path 1, plus the integral from B to A. I'm now closing the path, but this time I am going along path 2. This should be 0. So the integral of there's no loop. As I go from A to B along path 1 of dq by t, minus, if I change the limits of integration, there's a sign change. The integral from A to B along path 2 of dq by t, this should be 0. So the integral of dq by t along path 1 is the same as the integral from a to b of dq by t along path 2. So that integral is independent of how you go from point A to point B, which basically tells me that this integral depends only on the endpoints. If you don't change the endpoints, that integral doesn't change. So that basically tells me that I can always write that as the difference of a value that I can assign to, or difference of the values that I can assign to endpoints. Just like the potential. I mean, if you know that the work done along a closed loop is 0, you can just integrate the work from some point to some other point. That work will be independent of how you go from the initial point to the final point, and that integral you can call it as the change in the potential energy in mechanics, in forces. Basically the same thing over here. That integral of dq over t between two macroscopic states of my system, that means different two states with having different PMV, that integral only depends on the initial and the final point and nothing else. So that is our thermodynamic potential, if you like. Now we will keep calling these things as thermodynamical potentials, just mainly because we have a similar case in mechanics. In conservative forces, more or less the mathematics is the same.
This is only bad for the reversible process.
Yes. What happens if it's not reversible? What happens, let's say, as I said before, we have a piston, I just push it and create a shock wave. That is the second law of thermodynamics. In an arbitrary process, that is no longer 0, but can be less than 0. This is the second law. Which, by the way, is the same thing as in an isolated system. The entropy can either remain the same or increase. I emphasize this in an isolated process. Well, how are these two related? Well, let's say that I have a system. Let's say it might be, I have a piston. I just release the piston, and suddenly it expands on its own. This is an isolated process. So the piston starts from point A to point B. This is the PV diagram. Well, during the process, I cannot always talk about the pressure of the system. Well, the volume maybe, even that is questionable. But let's say that I show the evolution of my system from state A to state B through this dashed line. Since it's not an equilibrium process, it doesn't need to have the same pressure throughout the volume. So that's why I cannot really show the evolution of the system in this PV diagram. Now, in order to be able to use the second law, I have to imagine a closed loop. Let's say that I have my piston. I just move my hand suddenly, so the piston expands on its own spontaneously, but then I stop it. During that expansion, it's an isolated process. This is one process. Or I can imagine just slowly releasing the piston. This will be an equilibrium process. So during that slow release, I can talk about the pressure. At each moment it will have a pressure, etc. So it will follow some trajectory in the PV space. This is irreversible part. This is the reversible. So imagine these two processes. Now the second law of thermodynamics tells me that as I go around this loop, this should be 0. This should be less than or equal to 0. Well, let's say around this loop, I can imagine it as I go from A to B through the irreversible part. And then I go from B to A through the reversible part. This should be less than or equal to 0. Or if I move the second term to the right-hand side, there will be a minus sign. I want to get rid of that minus sign by just changing the limits of integration. So I have from A to B over a reversible process. This should be greater than or equal to through the irreversible part, again from A to B. Now, in an isolated process, dq is 0. So the right-hand side is 0. The left-hand side, since it's an integral over a reversible process, it's independent of how I go from A to B, and in fact it is defined as SP minus SA. That is how we define the entropy.
The adiabatic process in the isolated process?
No, it's not isolated. You see, adiabatic process is an equilibrium process. It's not necessarily adiabatic, but isolated. There's no heat exchange with the environment. It doesn't give heat, it doesn't take heat. Now, the left-hand side is the definition of entropy, the change in the entropy as I go from A to B. The right-hand side is 0, or SB is larger than or equal to SA. So you have to imagine an isolated process. There's no heat given to the system. There's no heat taken from the system. You just isolate the system, and something happens inside the system. During that process, the system need not be in equilibrium. It just happens on its own. If it happens on its own, the entropy of the system will increase. B, remember, is the final state that the system reaches. So during this process that happens on its own, the entropy increases. Now, if we go back to this definition, let's say that these states A and B of my system are very close to each other. So the change in the entropy is also very small. So that will tell me that ds, the change in the entropy, now this is a differential. This is equal to dq by dt, dq by t. Or what I'm more interested in is dq is tds. Now let's combine this with the first law. The first law tells me that delta U was delta Q minus delta W. The change in the internal energy for two very nearby states of the system, let me call it du, will be, well, delta Q is just TdS. Delta W, the work done by the system, we just said that it's PdV. So this is a relation between the differentials of internal energy, entropy, and the volume of my system. Now, when in our earlier hour, I said that thermodynamics gives us relationships between the macroscopic variables. So, for example, now I can already tell some of those relationships. Entropy is a macroscopic property. Volume is a macroscopic property. U is a macroscopic property. But if I, let's say, keep the in a process, if I keep the volume constant, so dV will be 0, T will be equal to du by ds, derivative of how fast the energy changes as a function of entropy, assuming I keep the volume constant. You see, this is valid for any system, not just Carnot engine, not just for ideal gas, it's for whatever system you can imagine. If you can somehow measure how the internal energy changes as a function of entropy at a constant volume, that gives you the temperature. Well, entropy is not so easy to measure, so this has limited practical use, let's say, but we will obtain other relationships that are more practical. Or I can assume I keep the entropy constant, I isolate my system, ds is 0, there's no heat exchange. And again, just keep in mind that for this relationship to be valid or meaningful even, my system has to be in equilibrium at each step of the change. I will be always talking about changes in which my system will, at each step, my system will be in equilibrium. I'm slowly changing the volume so that I can talk about the pressure throughout the volume. It will be have a uniform volume. I am slowly heating my system so that the temperature will be the same throughout the system at all steps. If these are satisfied, then this relationship will hold. Because otherwise, if the pressure isn't constant throughout my system, what is the P over there? It just does, this equation basically doesn't make any sense for such systems. Anyway, T is given by this expression. Well, I can imagine a system where the entropy is constant. Entropy doesn't change, so ds will be 0. So pressure will be minus du by dv. Again, I repeat, this is a relationship that relates changes in the volume, changes in the energy, changes in the entropy, and the pressure. And this equation is valid for any system that you can imagine. Well, let me go one step further. Let me take the derivative of temperature with respect to volume at constant entropy. Well, this will be equal to derivative with respect to volume at constant entropy of derivative of internal energy with respect to entropy at constant volume. Well, second derivatives of nice functions, and in physics we are always assuming our functions are nice. They will be nice almost always. Well, the second derivatives, the order doesn't matter. If you take the second derivative of a function with respect to its different arguments, you can just take that derivative in whichever order you want. It should give you the same answer. What that means is I can just change the order of differentiation with respect to entropy and differentiation with respect to volume. Well, that will give me derivative with respect to entropy at constant volume of derivative of internal energy with respect to volume at constant entropy. But now that derivative with respect to entropy is nothing but the pressure, minus the pressure. So this is minus the pressure. So derivative of temperature with respect to volume at constant entropy, yes, you can also read this as the dependence of temperature on volume in an adiabatic process, because adiabatic process is a process that keeps entropy constant. That's the more precise definition of an adiabatic process. The entropy should be constant. This is equal to minus the derivative of pressure with respect to entropy at constant volume. You see, now thermodynamics allowed us to relate the variations of well, almost completely in the arbitrary quantities to each other. And again, I repeat, this relationship is valid for any system that you can imagine. It should be valid for every system. This is so-called the Maxwell relation. One of them. We have other ones. And this relationship basically is based on the fact that there is a function of state U that can be expressed in terms of a function of state S, another function of state V. Just their existence tells me that their derivatives should be related in this form. Well, it doesn't tell me how the temperature of an ideal gas changes as a function of volume in an adiabatic process. For that, I need statistical mechanics. But I know that whatever that change is, it should it should be equal to the change of pressure as a function of entropy in an, let's say, in a process in which the volume is constant. Well, as I said, this is not so useful because, I mean, controlling the entropy, measuring the entropy is not such an easy thing. So what we usually measure, we can measure the temperature more easily. So I would rather treat the temperature as my variable and keep entropy as something I derive from other properties. Well, I can use a mathematical trick. Let's look at the differential of dTs. This is TdS plus SDT, but that means TdS is actually differential of Ts minus SDT. Well, why will this be useful? Well, du is, remember, TdS minus PdV. But TdS is differential of Ts minus SDT. If I move it to the left-hand side, the difference of the differentials of two functions is the differential of the difference of these functions. And U minus Ts is what we call the free energy, phi, F. So the differential of the free energy is minus SDT minus PdV. Well, I can basically do the same tricks that I did before. For example, the differential derivative of free energy with respect to temperature at constant volume. Since I'm keeping volume constant, dV is 0. If I divide both sides by dt, what I get is minus S. This is minus S. The derivative of free energy with respect to volume at constant temperature. Well, if temperature is constant, that means the dt is 0. It's not changing. dt is constant. If I divide both sides by dv, I get minus p. Now I can obtain the second differentials. I can look at the second differentials, which will give me a relationship, second derivatives, which will give me relations between the derivatives of entropy and the pressure. So, for example, derivative of entropy with respect to volume at constant temperature, it will be the second derivative of free energy with a minus sign. Change the order of derivation. But this is nothing but minus the pressure. So derivative of entropy with respect to volume at constant temperature will be derivative of pressure with respect to temperature at constant volume. Here there is a nice property. You see, look at the right-hand side. Pressure, temperature, and volume. Look at this. Given a system, you can keep the volume constant. Just don't allow it to expand. Give some heat so that its temperature changes. And as the temperature changes, you can measure the pressure that you need to apply in order to keep the volume constant. The right-hand side is quite easy to measure in a practical system. But that gives you how the entropy of the system changes as a function of volume at constant temperature. Entropy is not so easy to measure for a given system. But the right-hand side is easy to measure. So, for example, we know the ideal gas, equation of state of the ideal gas. Well, this tells me that the pressure is equal to Nk over V times T. Well, dP by dt at constant volume is actually Nk over V. So that this second Maxwell's equation, this is another Maxwell's equation, it tells me that derivative of entropy with respect to volume at constant temperature is equal to Nk over V. Well, I can integrate both sides over V. If I integrate both sides over V, it tells me that the entropy of the ideal gas is N times K times logarithm of V over, let's say, some reference volume plus some constant. You see, the constant, its derivative will not change the derivative of entropy. But there is one thing you have to keep in mind. Temperature is constant in this derivative. If temperature is constant, I should add some function of temperature over here. This is the solution of this equation. Entropy, this is the entropy as a function of temperature and volume, should have that form. Still, we don't know what the temperature, what that function of temperature is, but for an ideal gas, we know the volume dependence at a given temperature. How did we do that? Well, we know the equation of state. And in fact, for any system that has this equation of state, the entropy should have this form as a function of temperature and volume. Well, there are other things you can play around with. You see, with du is equal to minus s dt minus p dv. You can look at the differential of u plus pv. This is equal to minus s dt plus v dp. Or you can look at u plus s dt st plus pv. No, sorry, this is tds. Minus ts plus pv. This will be minus s dt minus plus v dp. This is the enthalpy. This is the, I think it was the Gibbs free energy. The other one is the Helmholtz free energy. And basically you can just play the same trick. This will tell you that the temperature, if this we call it H, temperature is del H by del S at constant pressure, volume is, etc. You see, for example, for gases, it's easy to keep the volume constant. You just don't let it expand. But for solids or liquids, it's not easy to keep the volume constant. If you heat it up, they will expand. If you want to keep the volume constant, you have to exert an enormous pressure. So for liquids and solids, it will be easy to look at thermodynamic potentials, where you assume you keep the pressure constant, like the enthalpy. That is why enthalpy is used in chemical processes. In chemistry, if you remember your chemistry courses, you dominantly work with the enthalpy, because If you have a liquid, you do a chemical reaction inside your liquid, it's exposed to the atmosphere atmospheric pressure is constant, so you are keeping the pressure constant. If the liquid is heated up, its volume will change, keeping the pressure constant. So in that case, enthalpy will be more relevant. Any questions?
Hocam, is there a reason that we call them as free energy? I mean, instead of gives energy and transforms energy, we call them free.
Well, let's see. The reason is basically, for example, look at this one. If you keep temperature and volume constant, dF is 0. So once the equilibrium is reached, dF will be 0. So equilibrium is an extremum point of free energy. And well, just like entropy is maximized in an isolated process, in processes at constant temperature and volume, free energy is minimized. So basically, you are extracting as much free energy as possible so that it is minimized during the evolution of the system at constant temperature and volume. The other free energy, well, this is at constant temperature and pressure. That's the available energy you can extract from the system. You cannot extract all of the energy, but some of it. That is why it's called free energy. It's free to be used for other products or something useful. Now we are tired, but let me just do one more simple computation. Let's ask this question. I said that for an ideal gas, U is equal to 3/2 nKT. Okay. So just using the equation of state, can we show that the internal energy of the ideal gas does not depend on the volume? And it only depends on the temperature. That is what I am asking. So I want to show that the free energy of an ideal gas, or for a gas that satisfies PV is equal to nKT, implies that U is independent of V and depends only on T. Let's see. If you think in terms of changes, what I would like to show, whether or not, what I would like to calculate is how much U changes as I change V, keeping T constant. But you see, this is nothing but derivative of U with respect to V at constant temperature. If internal energy depends only on temperature and not on V, then this should be 0. So basically, my question is whether this derivative is 0 or not for a system that satisfies this equation of state. Well, I know what delta U is. This was TdS minus PdV. Let me divide both sides by dV. Keeping temperature constant. Minus P. But I have already seen what this is equal to. You see, ds over dV at constant temperature should be equal to dP over dt at constant volume. Well, this equation should be valid for any system. Again, look at the right-hand side. Pressure, temperature, and volume, that derivative can be evaluated once I know the equation of state of the system. Whatever the system is, once you measure the equation of state, you can calculate the right-hand side, so you know the left-hand side. For the ideal gas, P is equal to NKT over V. In particular, dP by dt at constant volume is NK over V or P over T. But that tells me that T times dP over dTV is equal to P, or T times minus P is equal to 0. But this is nothing but. So as long as you have a system that satisfies the ideal gas equation of state, its internal energy depends only on the temperature and it doesn't depend on the volume of your system. Yeah, kind of this is the power of thermodynamics. It gives you relationships between thermodynamic properties. If you measure one thing about the system, then you can calculate lots of other properties of your system without knowing any microscopic property. Any questions? Any last minute questions? Well, I don't put an official office hour, and my office is right over there. If you have any questions, you can write to me, or you can just come by my office. And don't worry about disturbing me, because when I don't want to be disturbed, I just lock my door and ignore any knocks on the door. So feel free to come. So see you on Wednesday. Okay, Wednesday.
Hocam, are you going to continue with the review of thermodynamics?